Hey all, so today we are doing lesson 2.3, which is about graphing and evaluating piecewise functions. So go ahead and write that down. We have talked briefly about piecewise functions back in chapter 1. We just started an introduction to how to evaluate them, but today we'll go in a lot more depth just about how to graph them. Okay, so like I said, we're going to be able to graph, recognize, evaluate piecewise functions, and solve application problems. So go ahead and attempt this warm-up. This is a review of the last couple lessons we've been doing. All right, and then once you've attempted that, you can come back and look at the work that we've done here. So f and then this little O symbol, OG, means f of g of x. So we're plugging function g of x into function f. If you want to rewrite this as f of and then write out what function g of x actually is, you can totally do that. So this is what we're going to be plugging into function x. So sometimes I like to show students this, especially if they're just struggling with what am I plugging in where. Okay, so we're plugging in that entire thing, 2x squared minus 4x minus 2, into function f. So I will replace x with that. So 8 times 2x squared minus 4x minus 2, and then all of that minus 9. Okay, and then we simplify. So we've got to distribute this 8. We get 8 times 2x squared, which is 16x squared. 8 times negative 4, which is negative 32x. And then 8 times negative 2, which is negative 16. And then we combine our like terms. So negative 16 minus 9 gives us a negative 25. So 16x squared minus 32x minus 25. Okay. And then f minus g of x is the same thing as f of x minus g of x. So we're just subtracting the functions. So we get 8x minus 9, that's f of x, minus g of x, 2x squared minus 4x minus 2. Remember to put both functions in parentheses when you first start. And then we have to distribute this minus sign because we're subtracting the entire function. So we have 8x minus 9 minus the 2x squared. Minus a negative here becomes a positive 4x. And then same thing, minus a negative here becomes a positive 2. And then we just have to rearrange, put this in descending order of exponents. The highest exponents come first. And combine our like terms. So we've got 8x's and 4x's we can combine. We also can combine the negative 9 and the 2. So I'm going to rewrite the negative 2x squared first, because that's the highest exponent. Remember, you have to carry the sign out in front with that. And then 8x plus 4x is 12x, and then minus 9 plus 7 is minus 7, or minus 9 plus 2. There we go. Okay, so moving on to today's stuff. A reminder of the definition of a piecewise function. I know that, like I said, we've touched on this a little bit so far in this class, but I do want you to write this down again just as a refresher. So piecewise functions are functions that are defined by 2 or more equations over a specified domain. So you've got multiple equations instead of just one for piecewise functions. Okay, so also refresher on just how to evaluate piecewise functions. This just means that we are plugging in numbers. Here's a piecewise function with 3 different equations. So f of x equals the equation x squared when the domain right here on the right side, so these are the equations, and then these are the domains, when the domain is just x is less than negative 3. So any numbers that are less than negative 3 for x, they apply to this equation. The second equation is f of x equals x plus 4. That's when x is between negative 3 and 2. And then the third equation is when f of x equals x minus 1, and that's when x is greater than 2. So let's find these 3 values. So f of negative 5, the first thing that you have to determine is where is that domain. So negative 5 is less than negative 3. Which means we're going to have to use this first equation. So let me use a different color for that. It's in this. So we're using x squared, f of x equals x squared. So we just plug in negative 5 and square it, which gives us 25. Okay, the second one is f of 0. So now we evaluate, well, where is 0 in the domain? So 0 is between -3 and 2. So we're going to use this equation, the second one. So 0 plus 4, and that gives us 4. And then last but not least, f of 4. Again, we evaluate where is 4 in the domain. Well, 4 is greater than 2, so we're going to use this last equation. So 4 minus 1, plug that in for x, we get 3. Okay. So let's now review how do we find the answers or the solutions if we're doing a piecewise function application problem. So given this function, c of t equals 20 for a domain of 0 to 60, or c of t equals 20 plus this whole thing for a domain of t is greater than 60, we're going to find c of 40 and c of 80. Now this one doesn't really tell us what c of t represents. Likely t is representing time or something along those lines, and it represents the exact same thing, or we have the exact same process as with the previous slide. Okay, so if we plug in c of 40, we still need to evaluate where is 40, what part of the domain is that in. So is it between 0 and 60, or is it greater than 60? Well, 40 is between 0 and 60, so that means we're going to use this top equation, c of t equals 20. Well, if you notice, there's no x here, and because we can't plug in an x, and this is just a constant, no matter what, c of t equals 20 between these values, that just means c of 40 also equals 20. Okay? And then c of 80, same thing, we evaluate where is this in the domain. Well, 80 is greater than 60, so we would use this second equation here. So we'd plug in 20 plus 0.4 times, plug in the 80 here for x or for t, so 80 minus 60. Then I'd have to simplify what's inside the parentheses. So 80 minus 60 is 20. My brain's getting ahead of my words. Okay, and then 0.4 times 20 is what I multiply next. Order of operations says I multiply first before addition. So 0.4 times 20 is 8, and then 20 plus 8 is 28. Okay, so the key thing here with piecewise functions is really you just have to determine which equation by looking at the domain. So determine which equation you're plugging it into by looking at the domain. Okay, so that is, again, all refresher. Now we're going to talk about graphing piecewise functions. We looked at some graphs of piecewise functions, but we didn't actually graph them ourselves. So step number 1, I want you to write this down, is to make a table for each equation, starting with the boundary point. So the boundary point, what that means is where the domain starts or stops. Okay, so we're going to start with the boundary point, set that up in our table for each equation, and then we will move on to graphing. So here in example number 1, we've got this function f of x equals 3 if x is less than or equal to -1, and f of x equals x minus 2 if x is greater than -1. So we're going to set up 2 tables here, one for f of x equals 3, and then one for f of x equals x minus 2. And I'm going to label them at the top. That way I don't get confused. Please always do this when you're doing your own work as well. That way you can remember which one's which. And you can even draw them in different colors if you want to, or put a different asterisk by it for when graphing. Okay, so if we look at the boundary points here, f of x equals this function 3 for the domain that is x less than or equal to -1. So if we think about less than or equal to -1, that's starting at -1 and going to the left on a number line. So all of those negative values that are further negative than -1. So -1 really is the starting or stopping point. That is our boundary point for f of x equals 3. Okay, so it's going to start at -1. And then we want to go to values less than that. So we need at least a couple of values since it goes on to infinity. So let's just do -2, -3, -4, something like that, okay? And then for the second one, f of x equals x minus 2, this is starting at -1, and it is going to the positive values that are greater than -1. So -1, 0, 1, 2, 3, etc., stuff like that, or values like that. So -1 is the boundary point for both of these. The next thing I want you to make a note of in your table, so that this helps you when you graph, is it going to be a hole or is it going to be a point at that specific boundary point? So you know that it's going to be a point. This is just a reminder over here. It's going to be a point if it has an equals sign in the inequality, okay? It's going to be a hole if it's just a greater than or less than symbol. So the equal sign would be greater than or equal to, or less than or equal to. So if it's one of those, if it has the or equal to symbol, then it's going to be a point because it can exist there. So here at -1 for this first function, this would be a point. So you can either write a point or you can draw a point like that. Either one, just make a note to yourself. But then for this second one, x is greater than -1. That means at this specific value, -1, it's not going to exist there, so it's not going to be a point, it's going to be a hole. So you can draw an open circle or you can just write a hole, okay? So then we've got to just plug in these couple values for the table. Like I said, you always start at that boundary point, and then you want a couple of other points depending on which direction it's pointing. Now, technically, both of these are equations of lines, and for lines, you really only need to graph at least 2 to 3 points. So that's another thing that you can make a point of or note of. Lines only need at least 2 points. I would always graph just like 3 or 4 to be safe, but if it's a quadratic, if it's anything like a curved function, curved functions or other functions need at least 3 points to be able to see the shape, okay? The more points that you have, honestly, the better off you are, so that's why I added multiple points here. And then you're just going to plug these values into the equation. So here, for this first one, f of x equals 3, well, that's a constant, so there's no x there, and that means no matter what I plug in, -1, -2, 3, 4, all of those are always going to give me an output of 3. So 3, 3, 3, 3, okay? And then over here, for f of x equals x minus 2, I can just plug in, and I'm going to just erase some of these right here so I have a little bit more room. I can just start plugging these values of x into the equation here. So you could do this over to the side. F of -1 would be -1 minus 2, which is -3. F of 0 would be 0 minus 2, which is -2. F of 1 would be 1 minus 2, which is -1. And f of 3 would be 3 minus 2, which is 1. Did I skip 1? Yeah, I skipped 2. So we can do f of 2 equals 2 minus 2, which is 0. All right, so -3, -2, -1, 0. Okay, and then we're going to plot those. I'm going to draw f of x equals 3, this first one in pink, and then the second one in green. So we're going to plot the points -1, comma 3, -2, comma 3, -3, comma 3, etc. And we know that this is pointing to the left forever and ever and ever on to -infinity, because the domain is from -1 and then all the way to -infinity. And we just plotted these first couple of points, okay? And then this next one, we are starting at the point -1, comma -3, but that's going to be a hole. So -1, -3, put an open circle there, and then let's plot the next couple points. So 0, -2, 1, -1, and 2, 0. And we know that that's going to now point to positive infinity forever and ever because its x is greater than -1. So that is our piecewise function. Okay, example number 2. we've got a new function here. Go ahead, take a minute to write it down. And then we're going to set up our two tables. And label the first equation as f of x equals 3x plus 2. Second equation is f of x equals x squared minus 4. Okay, then we look at our boundary points. So this domain here for the first equation is x is less than or equal to 0. So it's starting at 0 and pointing to the left. So 0 is going to be our boundary point. And then values to the left of that would be -1, -2, -3, etc. This one is the equation of a line. So even though I technically only need at least 2 points, like I said, I'm just going to do a couple extra points just to be safe. Okay, and then this next one has a domain of x is greater than 0. So also has a boundary point starting at 0, except this time it's just greater than it. So we need to make a note that that's going to be a hole. Okay, so over here, I'm going to make a note that this first one is a point because it can equal 0, but then this second equation has a hole because it is just greater than 0. So we'll pick a couple values to the right of 0, 1, 2, 3. This one is a quadratic, so you see the x squared minus 4, that means because of the U shape, we definitely need to do more than 2 points. So we have to have at least 3 or 4 points for that one. Okay, so then over to the side, we'll just plug these values in. So f of 0, I would get 3 times 0 plus 2, which is just going to be 0 plus 2, which is 2. Okay, then f of -1 would be 3 times -1 plus 2. That gives me -3 plus 2, which gives me -1. Then f of -2, which is 3 times -2 plus 2, which becomes -6 plus 2, which is -4. And then f of -3. I know I'm going through this kind of quickly, so feel free to pause the video. Okay, and then that gives you -7. All right, so we've got those values. And now let's go ahead and plug in the values for the second table. So now we've got f of 0, we're plugging that into x squared plus 4. So 0 squared, oh sorry, that's a minus 4. So 0 minus 4, which is -4. Then f of 1, so 1 squared minus 4. 1 squared is 1, minus 4 is -3. Then f of 2, so 2 squared minus 4. 2 squared is 4, 4 minus 4 is 0. And last but not least, f of 3, which is 3 squared minus 4. 3 squared is 9, and 9 minus 4 is 5. Okay. So then we're going to plot these. I'll plot the first one in pink like I said. We're starting at 0, 2. Okay, there is a point there. Then -1, -1, then -2, -4, then -3, -7. Go back and check your domain. Okay, so starting at 0 and then going to -infinity, so less than or equal to 0. So I know that it's going to continue on to the left. So I'm going to put an arrow to the left and it stops there at 0. All right, and then this green one, let's plot this. So 0, -4. That is a hole, so make sure it's an open circle. 1, -3. 2, 0. 3, 5. Okay, now notice this one, remember, is a quadratic. It is not a line, so it should have a U shape. And this is going to point forever and ever and ever onto the right and upwards because it is greater than 0. And so we're seeing obviously only about half of the parabola right now. The other half is probably on this side. Okay, writing the equation from a piecewise function. This is another thing that you're going to practice on your homework. So we are given the graph here. You can pause the video, take a moment to draw this. You do not have to have every single point, but definitely the main boundary points and the general shape. So quick reminder, because a lot of these graphs that you guys are going to see, if we have you write the equation, likely it's just going to be the equation of a line. So slope-intercept form of a line, as a reminder, is in the form y equals mx plus b, where m is the slope, or rise over run is what we call that, change in y over change in x. Okay, and b is the y-intercept, and where it crosses that y-axis. So you're going to need this just so that you guys can figure out what these equations are. The other reminder is that a horizontal line is always written in the form of y equals whatever value that is, okay? Whatever that value is at the y-axis. And you're also going to see quite a few horizontal lines on these. So let's take a look at this very first equation here. Okay, we'll deal with the domain in a second, but for now we just want to figure out the equation. So I know that this is a line, and the first thing that I'm going to try to determine is a slope, and then I'll find the y-intercept. So to determine the slope, you want to find a point kind of on the left side of the graph, and then you want to find the next nearest whole number point. What I mean by that when I say whole number point is one that's on a corner of the grid or the graph, not that's like in the middle. So if I look over here, like that's in the middle, and I'd have to estimate this is in the middle, and I'd have to estimate. So I want to go to the next nearest whole number point. So if I go here to that point, that's on a corner, and then I have to determine how much does the line have to rise and then run, or go up and then over to get to that next point. So it goes up 3 over 2, okay? If you continue that pattern, if that's the slope, 3 over 2, then we want to go all the way up to where it crosses the y-axis to see what the y-intercept's going to be. So go up from this point, 1, 2, 3 over 2. Okay, this is where it would cross. And that's at the point 0, 1, 2, 3, 4, 5. So we've got our y-intercept and our slope here. So we would write y equals 3 over 2. So up 3 over 2, that's rise over run, times x plus 5, which is where it crosses the y-axis, 0, 5. Okay, then let's look at the next one over here all the way to the left. So this one's decreasing. It's also a line though, so I'm going to find the slope first. So I can start at this point on the left, and then we want to go to the point on the right. Again, we always do that because we read graphs left to right like we read books. So this is the next nearest point that's on a corner, and then this one. And I want to make sure it's consistent. So this goes down 2 over 1. Down 2 over 1, down 2 over 1. So that's consistent. Okay, so the slope here is going to be negative 2. And then we'll multiply that times x and add it to the y-intercept. So I have to work my way backwards to get to the y-intercept. So instead of going down 2 over 1, I do the opposite. So go up 2 over 1 to the left, up 2 over 1 to the left, up 2 over 1 to the left. So technically that's off the graph a little bit, but only by 1, so we can count that still. So 1, 2, 3, 4, 5, 6, 7. So 0, 7 is that y-intercept. Okay, so y equals negative 2x plus 7 is going to be that equation. And then last but not least, let's look at this horizontal line. So this is at the y value. If I look at my y-axis, this is at the y value of 1, 2, 3, 4. Okay, so this is the equation y equals 4, because all along this horizontal line, x is changing. So x is at negative 2 here, it's at negative 1 here, it's at 0 here, 1 here, 2 here, even though there's a hole, it doesn't exist. Okay, but the y value stays the same at 4. So now let's put all the parts and pieces together and write our piecewise function. So we write f of x equals, we've got this curly key bracket, and we are going to write all 3 of these equations. So 3 halves x plus 5, and then we'll write it left to right, 4, because that's the next one, and then the green one here, negative 2x plus 7. And then we have to look at the domain. So if I look at the domain, I am concerned about the x-axis here. So what are the x values? So this x value is -2, and there is a hole there, and then it's pointing to the left. So x is less than -2. It does not equal 2, though, because of that hole. Then if I look at this horizontal line, this is starting at x equals -2, and it's going really, really, really close to where x is 2 right here, but there's a hole at 2. So it's between -2 and including -2 and 2, but not including 2. So it's going to be a double inequality like that. And then here, the last one, this starts at 3, so when x is 3, and goes all the way to positive infinity. So x is greater than or equal to 3, and it can equal 3 because there's a point right there. So that is how you would write the equation from a piecewise graph. Like I said, we're just going to give you lines, so you won't be having to deal with quadratics or anything like that quite yet. Okay, one more thing to go over, just briefly. You're not really going to do a ton with this in college algebra, but we just want to expose you to it a little bit because you will see it in pre-calc if you go into pre-calc next year. So step functions, they are a special type of piecewise functions. So go ahead and write down this definition. Step functions, sometimes we call them staircase functions. They look a lot like a staircase. It's a step function with all constant pieces or equations. When I say a constant equation, I'm talking about one that looks like this blue one on our previous graph, okay? So if it's constant, that means it's staying the same. It's that horizontal line, and it is not changing. That y value is not changing. And step functions will always be discontinuous. What I mean by that is that you're going to have to pick up your pencil to draw the function. So you cannot just draw the entire function without picking up your pencil. It'll be discontinuous, meaning it's going to have multiple parts and pieces that you're going to then have to pick up your pencil or pen for to draw. Okay, so let's look at some examples. Here's one example. So we've got f of x equals 4 equations right here. The constant function 1, 2, 3, and 4 for these different domains, okay? So notice it equals the constant f of x equals 1 right here from 0 to 1, not including 1, and then changes to 2, and then changes to 3, and then changes to 4. So that's kind of why it looks like that staircase, just because of the behavior here, that it's all constant functions, 4 of them, and all for these limited domains. Okay, here's another example. So this one's f of x equals -3. So down here when y is -3, from -2 to -infinity. All right, and then here's another little stair step from -2 to 1. And then here's a third stair step from 3 to positive infinity. So you'll definitely see a couple of these or practice them. All right, and then there are 2 special types of step functions that we'll talk about very briefly. And these appear all the time in real life situations. So the first one's called a ceiling function. In a ceiling function, kind of like what it sounds like, all non-integers, so remember integers, we talked about this at the very beginning of the year, are positive and negative whole numbers. So negative infinity, not negative infinity, but it can go all the way there. So -3, you could have -2, -1, 0, 1, 2, 3, ... onwards, okay? So when all non-integers, okay, anything that's going to be like a decimal or a fraction or something like that, if it's rounded up to the nearest integer, that's what we call a ceiling function. So an example is when a phone service company charges by the number of minutes used and always rounds up to the nearest integer of minutes. So let's say you're on the phone for 2.53 minutes. They're probably not going to bill you for 2.53 minutes. They would round up to bill you for 3 minutes instead, okay? So this happens all the time when you go up to the next nearest integer value. That's why it's called a ceiling function. So if you take a look here, this kind of shows you this graph or this example. This just shows you, okay, if you jump from the integer 1 to any decimal, any value in between 1 and 2, so 1.11, 1.5, 1.9, they're going to round that up to 2. All right, second special step function is a floor function, and this is the opposite of a ceiling function. So it's when all non-integer values are rounded down to the nearest integer. So an example, the way that we usually count our age is an example of a floor function, since we round our age down to the nearest year and we don't add a year to our age until we have passed our birthday. So for instance, when you are born, you technically don't say, oh, this baby, or you are 1 year old, until you've actually had a full year of life. So you might say, oh, the baby's 5 months old. You're rounding down instead of rounding up to the nearest age, which would be 1 year. Or if a baby is 1 year old and 2 months, we round down to just say that they're 1 year old. Okay? So that's an example here. And similar to the previous one, except now the points are on the left because you're rounding down to that next lowest integer. Okay, again, ceiling and floor functions you're not really going to be dealing with throughout this chapter or this year much. You might see them occasionally in examples, but we just want to expose you guys to those for now. Okay, so your homework today is another worksheet. It's called the 2.3 worksheet. If you have a printer at home, you can print it. If not, you guys can just write down the questions and then do it on your own separate sheet of paper and ask us if you have questions.